All right, let's talk about a situation every single one of us has been in. You're looking at a chart, you see a jump in performance, and you have to ask, is that a real win or was it just a lucky break? Well, today we are decoding the exact tool that analysts use to tell the difference, to separate a true decisive signal from all that random noise.
And this is really the heart of the matter, isn't it? Maybe you launched a new ad or you tweaked your website's design. The numbers moved, great. But how can you be absolutely sure it was your action that caused it? How do you know it wasn't just the chaotic, random variation that exists in literally every data set?
And this gets us right to what we can call the analyst's core dilemma. It's this fundamental challenge for anyone who's trying to make smart, data-driven decisions. The question is, how do we act with confidence when we know for a fact that data is inherently messy?
I mean, think about it. No 2 days are ever exactly the same, right? Sales go up and down, user engagement ebbs and flows. All that randomness, that's the noise. The effect you're trying to measure, that's the signal. So our whole job is to confidently pull that signal out from all the background noise. Without a tool for this, let's be honest, we're just guessing.
And that is exactly where our tool comes in. To solve this dilemma, analysts and decision makers rely on a very specific statistical concept, the p-value. You can think of it as the standard, professional method for bringing real rigor to a decision.
Okay, that sounds a little academic, right? Let's unpack what it really means. In statistics, we always start from a place of skepticism. We call it the null hypothesis, which is just a fancy way of saying we assume our change did nothing at all. The p-value then asks a very specific question. Okay, assuming our change had zero effect, what's the probability we'd see results this good just by pure random chance?
And the answer to that question is always just a simple number, a probability, somewhere between 0 and 1. 0 means there's no way you'd see this result by chance, and 1 means it was basically guaranteed to happen anyway. This simple property is what makes it such a universal yardstick.
So now we have this probability. How do we turn it into a clear yes or no decision? Well, the process is actually surprisingly straightforward. We compare our result, the p-value, to a benchmark that we set before we even start the test, and that's the decision rule.
And this slide lays out the two key players perfectly. Over on the left, you've got alpha. Think of alpha as the goal line you draw in the sand before the game even begins. It's your pre-committed standard for what you'll consider a significant result. Then on the right, you've got the p-value. That's the actual result you got from your data. So the p-value is your evidence. Alpha is the bar for that evidence.
And this comparison is the heart of a really clear 5-step process. First, you set your alpha, your significance threshold. Step 2, you run your experiment. 3, you calculate the p-value that comes out of that data. Now, step 4 is the big moment. You compare them. And finally, step 5, you make a decision. If your p-value is smaller than or equal to your alpha, you've crossed the threshold. You can declare your results statistically significant. Okay, so that's the core framework. But to really make this stick, let's do a quick deep dive and just knock out some of the most common questions that people have about p-values.
All right, first up, this is the one you'll see everywhere, a p-value of 0.05. What is that actually telling you?
It's simple, really. It means there's only a 5% chance, or a 1 in 20 chance, that the results you're seeing were just a random fluke. And for most fields, a 1 in 20 shot is a small enough risk that we're willing to bet against it and conclude that, yeah, there's probably a real effect going on here.
Which, of course, leads to the next logical question. If a 5% chance of being a fluke is good, is a 1% chance even better?
Oh, absolutely. The lower the p-value, the better. A smaller p-value means the odds of your result being just random noise are even smaller. It's like having a much more convincing piece of evidence against that initial, skeptical assumption that nothing happened.
All right, what about the technical side of things? Are there any hard limits on what this number can even be?
And this is a hard and fast rule. Because a p-value is just a probability, it can never be negative, and it can never be greater than 1. If you ever see a p-value outside of that 0 to 1 range, it's a giant red flag that somebody made a mistake in their calculations. Now, you should know, p-values aren't without their critics, but they are still an absolute cornerstone of analysis. So you have to wonder, why have they stood the test of time?
Well, it really comes down to a few very practical reasons. In a world full of super complex models, the p-value is relatively easy to calculate and to understand. It's a single, universal metric that works across tons of different tests. But maybe the most important thing is that it's reproducible. If you and I have the same data, we should arrive at the exact same p-value, which creates a common ground for any debate. But this brings us to what is probably the single most important takeaway from this entire discussion. A p-value is an incredibly useful tool, but we have to be extremely precise about what it's telling us, and more importantly, what it isn't.
And this quote right here says it all. A low p-value might show a statistically significant link, a relationship between your new ad campaign and a rise in sales. It tells you that the association between the two is very unlikely to be just a random coincidence.
But, and this is the big but, it does not prove the ad caused the sales to go up. Maybe a competitor went out of business that week. Maybe there was a holiday. Who knows? The p-value is just one piece of evidence. You have to combine it with a well-designed study and some good old-fashioned critical thinking to get to the real truth.
So the bottom line is this. The p-value is our tool for finding the signal in the noise. It gives us a structured, disciplined way to evaluate evidence. So the next time you see a claim that X increased Y, you now have the framework to ask the most important question of all. Is that result statistically significant, or could it just be a fluke?